Good evening, everyone. Today we will start with the next chapter, electrophoretic techniques. Okay. If you look into the word electrophoretic over here, it can be broken down into two words. Electro, which means electric current, and the word phoretic, it comes from phoresis, which means separation. Okay. So the electrophoretic techniques, they mean that when we apply an electric current to separate the analytes which are present within a sample. Okay. So on what basis they are separated? They are basically separated on the basis of mass, charge, okay. Then mass, it is basically related with the radius of the sample, okay, or the analyte, sorry. And then we have size, okay. So this radius means usually we call it hydrodynamic radius, sorry, hydrodynamic radius. That means when a molecules they get solvated, and if we get a what do you call, if you have an analyte and over there is a hydration layer and it forms a radius like spherical like structure, then the radius of that spherical structure, the hydrated of the hydrated sphere or the hydrated molecules which is appearing as the sphere, it is regarded as the hydrodynamic radius. Okay. Then size also plays an important role, and charge on the molecules, they also play an important role. And then we have another important thing, this that is the strength of the electric current, strength of electric current or field, okay. And then viscosity of the medium, okay. So these are some of the important parameters which play an important role in the separation process, okay. Then there are two types of electrophoretic techniques. First type is zone electrophoresis, and the second type is moving boundary electrophoresis. Okay. So these are the types of electrophoresis. Okay. So this you need to know. Under the moving boundary electrophoresis, we have capillary electrophoresis. So for the rest of the chapter, I will be naming electrophoresis as EP. Okay, capillary electrophoresis. And in zone electrophoresis, we have gel electrophoresis. Okay, and there are other types of electrophoresis which are also available under this zone electrophoresis. Okay. Now let's see how it happens, because there are several techniques which are there, uh, which you will find that they are being used, or there are different types of what you call architectures for implementing this electrophoretic techniques. Now, one preliminary thing, when we discuss this electrophoretic techniques, you will find that it is similar to chromatography. Many of the techniques you will find they are similar to chromatography, but over here the separation is mainly due to the application of the electric field. So you will be able to correlate these chromatographic techniques with the electrophoretic techniques. However, you will find the ultimate what you call separation, it is being achieved only by applying an electric current or electric field. Okay, electric current means electric current is always associated with the electric field, so because V is directly proportional to I, right? So you may say electric, you are applying an electric field, you may say you are applying an electric current, both are the same thing. Okay. Now what is happening over here is that, as I said, the separation of the analytes that are present within a sample. So the analytes over here, as I said, they, if they have to be electrically conductive in nature, they should have a charge. Okay, and these analytes are quite commonly referred to as charged particles in terms of electrophoresis. Okay, so electrophoresis, it is the motion of dispersed particles relative to a fluid under the influence of a spatially uniform electric field. This is the important stuff. Electric field, we have to apply an electric field, and upon the application of this electric field, the dispersed particles within the system, so these dispersed particles, they are relatively they are charged particles, and they try to move through the fluid under the what do you call, under the effect of the electrical field. So this is an illustration of an electrophoresis technique. So suppose if you are applying an electric field, so we know that electric field, it varies from it is being generated from plus and it ends at negative. Plus means anode and this is cathode. Okay, plus is anode and the other thing is cathode. So yes, do you want to tell something? Okay. So the electric field, it gets generated at the anode and it is applied and it is generated at anode and it gets terminated at the cathode. Now we are having the electrical field from right to left in this case. Okay. Now when there are charged particles, say the cation, what this anode will do? This anode, it will push this charged particle, this cation, towards the cathode and while it is moving, what it is doing? It is taking the fluid around it. This is the fluid layer. Suppose this cation, it is solvated with this external, this dark layered fluid. Okay, so when this charge is moving under the electrostatic force, that means the electrical field, it is taking this solvated liquid along with it towards the cathode region. Okay, and it is quite possible that if this cation, it is associated with certain anions, then within this layer, those anions will also move, because what it is doing, this aqueous layer or the fluidic layer, it is also getting dragged along with this cation. Okay, so in this fluid we have these anions also. So these anions also, they start moving towards the cathode region. Okay, however, these fluids, since they do not have their own charge, then what it is happening, due to this, you are having a frictional force which is called the drag force. Okay, sorry, the retardation force is called the drag force, sorry, and which is trying to oppose this this electrical this movement, due to the electrical movement of the cations and the friction which is being uh, exerted by the capillary. So because of this, if you see, there is a frictional force, there is a backward force, and this backward force, it is due to the frictional force and the drag force which is being exerted by the liquid. Okay, your drag force is the lower one, not the frictional force. Okay, so the drag force and the frictional force, both of them, they are creating a counter, what do you call, it is restricting the movement of the cations towards the front side, towards the cathode. Okay, so you can see that there are two types of forces which are necessary, which are getting into the play during the movement of the charged particles within a system. Now, if you look over here, these forces, they are also dependent on the electrical field. So there is a critical limit, which is which needs to be achieved. Critical limit of what? Critical limit of the electrical field. So there is a critical limit of the electrical field which needs to be applied before, after which these cations or the anions, that I mean, in what you call, if you generalize it, if the charged particles, they start moving within the system. Okay, so you have to apply a minimum of an electrical field which will be needed. Otherwise, what will happen is that the total electrostatic force which is being applied over the charged particle, it will be counterbalanced by this frictional force and the electrophoretic retardation force. Okay, and then, as I was telling you, there are two types of electrophoresis techniques. The first one is zone electrophoresis and the second one is moving boundary electrophoresis. And the example of the moving boundary electrophoresis is the capillary electrophoresis. Okay. Now, electrophoresis of the positively charged particles, that means the cations, it is regarded as the cataphoresis, whereas for the anions, it is regarded as the anaphoresis. Okay. So as I said, the electrophoresis, it is used to separate macromolecules based on size and charge. The technique that applies a negative charge, so proteins move towards a positive charge. That means if you see in our body, the nucleic acid, the proteins, if you see over here, electrophoresis is extensively used in DNA, RNA and protein analysis. So what happens over here? These DNA, RNA and proteins, they are usually negatively charged ions. They are negatively charged. Okay. So if you need to apply the purification process, or if you want to separate or purify the DNA fragments or the RNA fragments or the protein fragments, then you have to apply a negative charge or a negative potential so that these particles, DNA, RNA or protein, they can move towards the positive charge. Okay. Now I hope everyone knows about this PI concept, ionization, this thing. So just I will tell you in a brief. Suppose you are having a scale. Say this is the pH scale. On the left hand side you are having, say, the pH of 1, and on the right hand side you are having a pH of 10. So you have a protein, say, which is having a PI of, say, 5. So in that case the protein will be positively charged, at the region 1 to less than 5. Okay. Then at PI it will be neutral, and at pH greater than 5 it will be negatively charged. Okay. So any compound, if it is a charged molecule, then it will definitely be having a PI. Especially it is true in for the case of DNAs, RNAs and proteins, where we have both amino group and COH group. So at PI equals to 5, so what will happen? This NH2 and COH will be present. If we go towards the acidic pH, so what will happen? This NH2, it will become NH3 plus. Okay, and COOH. Whereas if you go towards the higher pH, what will happen? We will be having NH2R COO minus, right? So that's why we are having at PI, we will be having both these amino group and the carboxylic group, both the basic and the acidic groups, they will be neutralized. Whereas at the lower pH, we will be having positively charged particles, and at a higher pH, we will be having negatively charged particle. I hope every one of you know about this. Okay. So I am not going into the details of this. Now, types of electrophoresis. We have capillary electrophoresis. Okay. The first type, commonly used to separate biomolecules by their charge and frictional forces. Then we have gel electrophoresis, a technique used by scientists to separate molecules based on physical characteristics such as size, shape and isoelectric point. Okay. Under this gel electrophoresis, we are having electrophoresis of nucleic acids, electrophoresis of proteins, 2D two-dimensional electrophoresis, and SDS page electrophoresis, where SDS stands for sodium duodecyl sulfate. Okay, and page, it stands for polyacrylamide gel electrophoresis. Okay. So there are two types of page. One is normal page, polyacrylamide gel electrophoresis, and there is another SDS page where we have sodium duodecyl sulfate, which is used to denature the protein so that the secondary structure, it is being broken down and we get a linear chain protein, and that helps us in understanding the linear, what you call, linear polymer chain length of the proteins. Okay, so it helps to analyze, to understand what is the linear chain length of the proteins, or you can say what is the linear molecular weight of the protein. Then we have affinity electrophoresis, which is used to separate and characterize biomolecules based on their molecular characteristics through binding to another biomolecule. Okay, and then we have immunoelectrophoresis, which is used to separate and characterize biomolecules on basis their molecular characteristics as well as binding of antibodies. Okay, so if you see, these two are somewhat interrelated. So in today's class, we will be basically restricting ourselves to the capillary electrophoresis. In the next class, we will be discussing about the gel electrophoresis, and in the last class on Monday, we will be discussing about this affinity electrophoresis and immunoelectrophoresis. So capillary electrophoresis, in short, it is regarded as CE. It is a family of electrokinetic separation methods which is performed in sub-millimeter diameter capillaries and in micro or nanofluidic channels. This is an important thing, sub-millimeter diameter capillaries. Okay, so it is basically when we talk about these capillaries, what is a capillary? Capillary, you will find it is a cylindrical structure. Okay, and we are having this diameter, which is the internal diameter of this tube, it is very small. In case of this capillary electrophoresis, it is approximately in the range of 10 to 100 micrometer. Okay, so you can see it is quite narrow. This capillary is quite narrow, right? As a matter of fact, the human hair, it is having a, what you call, a diameter of approximately 100 micrometer. Okay, so you can find out what is the you can compare what is the internal diameter of the what you call this capillary which is used for the capillary electrophoresis. Okay, very often C refers to capillary zone electrophoresis, but other electrophoretic techniques include capillary gel electrophoresis, capillary isoelectric focusing, capillary isotachophoresis, and micellar electrokinetic chromatography. Okay, which belong also to this class of methods. Okay. In C, analytes migrate through electrolyte solution under the influence of an electrical field. Okay, analytes can be separated according to ionic mobility and or partitioning into an alternate phase via non-covalent interactions. Additionally, analytes can be concentrated or focused by means of gradients in conductivity and pH. Okay, analytes can be concentrated or focused by means of gradients in conductivity and pH. Okay, so this is an important this is an additional thing which we can have. So basically, when you talk about this pH, analytes can be concentrated or focused by means of gradients in conductivity or pH. I can tell you an example of this pH. For pH, you will find IPG strips. What is IPG? I stands for immobilized pH gradient strips. Okay, so these are basically strips which is having a gradient pH. So one of the common strips, they have pH from 3 to 10. So you will be having 3 to 10. So 3, 4, 5, 6, in this way you will be having the pH. Now what you have to do? You have to apply your sample on the strip, and then you have to apply the potential across this strip. And when you apply the potential across this strip, according to the pH, the molecules, they will move towards the pi, where they will become this neutral, and they will be concentrated at that region. Okay, so in this way we can use the pH and the electrophoretic technique to concentrate or to focus the protein of our need at a particular stuff. So suppose this is basically used when, suppose we are having two proteins or two amino acids or two nucleic acids which are showing some similar characteristics. Okay, and even they have similar electrical conductivity property. However, so how will you differentiate those? You can differentiate it, but you know the properties, the pi of those nucleic acids or the proteins. So by using these IPG strips, you will be able to segregate or to separate the amino acids or the proteins. Okay. So this is a typical diagram of an capillary electrophoresis system. Okay. So in a capillary electrophoresis system, you will be having a source vial, okay, and you will be having a destination vial. Okay. Then these vials, the source vials and the destination vials, they will be interconnected with the capillary. Okay. At the cathode, near the cathode, the capillary will be having a detector. Now this detector can be an UV visible detector. Okay, it can be a mass spectrum analyzer. Okay, it can be IR spectrometry. So whatever you want, whatever detector you can think of, you can put it over here. Doesn't matter. Okay, the main idea is to quantify the analyte which is passing through the detector. Okay, now what happens over here is that when you apply this voltage, okay, suppose you are having cations over here, this sample vial, if you see the sample vial, it is having the cations. When you put it over here, so what will happen? You have injected this cations over here. Now when you switch on this power supply, so what will happen? It will push the cations towards the cathode. Okay. Now depending upon the charge and size, these cations will be moving towards the cathode. Now in a particular in a typical way, if you consider this thing which is showing the electroosmotic flow. So if you see, if you have two atoms but of similar sizes, say A1 plus and A2 plus, when you have these two, so what would happen? A2 plus, it is having the highest charge, and since it is having the highest charge, it has moved towards the cathode in a faster way. Then the atom or the cation which is having similar size but they are having a lower charge, they will be eluted towards the cathode. Then what will happen? Suppose then you are having two molecules or two cations which are having same charge, but the size is different. So the cation with lower size, that will be eluted first as compared to the cation which is having a greater shape. So from here we can see, if a molecule it is having higher charge, it will move faster, and if it is having lower mass, it will move faster, okay, towards the specific electrode. In the case of the neutral ions, they will be they will be present in the intermediate intermediate place, and after that again if you see, the highest charge, then the lower charge, then the larger size anion, okay. So towards the anode you will be having highest charge, lowest charge, and the larger size atom or the anion, okay. So over here what happens now? So what do we find over here? We find out that if we are having an electroosmotic flow, the anions and the cations, they will be rearranging within the cathode, within the capillary, okay. So how they will move? They will move based upon the electrophoretic mobility of the anion or the cation, which is given by mu, and this mu, it is basically a ratio of charge is to size, okay. Because if you see over here, what we have said, when the charge is high, mobility is high, when mass is low, mobility is low. So usually when the mass is low, your size is low. So we get mu is directly proportional to charge q, and it is inversely proportional to the size or the mass. So if we combine these two, we get mu equals to q by m or q by s. Size, I am considering mass and size, with both can be replaceable, okay. In many cases it can be replaceable, and in many cases it cannot, okay. But if we consider that both of them they are spherical in nature, then we can consider that the mass and the size, they will be similar, okay. So do you have any question till now?
No, sir.
So what is happening over here? It is due to the electroosmotic flow. This distribution is due to the electroosmotic flow, okay. Now when we put the sample within the capillary, it is intentionally kept at a pH greater than 3, okay. Now why that is so? Because if you see, the capillaries over here for the capillary electrophoresis, they are being made with fused silica gel capillary, okay, fused silica gel capillary. Now this fused silica gel, what happens is that they are basically SiOH group, this OH group, it is extended towards the internal surface. Okay. So when we keep the pH towards the higher pH, okay, say suppose this is 3 and this is 10, if and in between we have 7, so if we keep the pH towards higher pH, this group, OH group, it becomes O minus group, which is regarded as selenoid group. Okay, this is regarded as selenoid group. And the OH group, when it is in the OH group near to this 7 pH, it is having a selenol group. Okay, it is regarded as selenol group, SiOH. And when we keep it at a higher pH, it is usually kept at greater than 7. So though it is written over here that pH value is greater than 3, that means it is having a pI value of approximately 3. So maybe take it as 1, not this. So pI value of nearly 3. However, the pH of the buffer, it is usually kept towards the basic thing around 7.7, around pH of 7.7. So this is done so that this selenol group, which are fused over the internal surface of the capillary, they become charged. Okay. Now, when you have this buffer within the capillary, when you put this capillary within the solution, so what will happen? When you put it, due to the capillary action, this liquid will be pulled into the capillary and the capillary will be filled up. Okay. Now under this case, what will happen? Since we are keeping the pH at 7.7, these O minus groups will be formed. That means the selenoid groups will be formed. Over here, to neutralize the charge, the cations from the buffer, they will come and they will strongly bind to this O minus group. Okay, and that strongly bound layer, it is called the fixed layer. This strongly bound layer, it is called the fixed layer. Now over here, not all the selenoid groups, they are activated. Okay, or they are being covered. So what you find is that there is some extra number of O minus group or the anionic groups which are present in this fixed layer, this anion and cation layer, which is regarded as the fixed layer. Over there you will be finding some extra anionic groups, and because of that there is a secondary layer which is formed where you have both anions and cations However, what is happening? Due to the electronegativity of the selenoid group, there are some extra cations over here. Okay, so this layer is called the diffuse layer. They have a diffuse layer. Okay, now in this diffuse layer, what will happen? You will be having concentration of the cations will be greater than the concentration of the anions, and then within this region you will be having this bulk phase where the concentration of cation will be equal to concentration of the anions. Okay, and then you will be having again another diffuse layer, another, since it is circular in nature, the capillary is circular in nature, you'll be having another diffuse layer, you'll be having another fixed layer, and the capillary wall. Okay. Now, when you apply this electrical field and you apply through the anode and cathode, what happens is that fixed layer, as the name suggests, it will be fixed. However, the diffuse layer, where there is slightly higher number of the cations, they will be pushed. Okay, they will be pushed. So this layer and this layer, the diffuse layers, they will be pushed. So when they will be pushed, what will happen is that the bulk phase, they will start moving, and then the bulk phase, they would also start moving as a front. Okay, so there is an electrophoretic movement of the buffer from the anode to the cathode. Okay, so if you consider a stuff over here like this, if you have this capillary and then you have the fixed layer, in this case suppose this is a pocket of the buffer, then when you start applying this electric field, this will move towards the other end, and this is a continuous process. Okay, so this is a continuous process. So there is an active movement of the buffer from the anode to the towards the cathode. Okay, are you getting my point? So in this way there is the movement of this one, and apart from that there is also the electroosmotic field. Okay, so this is what it is. It has been explained over here. So electroosmotic flow is observed when an electric field is applied to a solution in a capillary that has fixed charges on its interior wall. Charge is accumulated on the inner surface of the capillary when a buffer is placed inside the capillary. In a fused silica capillary, silanol groups attached to the interior wall of the capillary are ionized to negatively charged silanoid groups at pH values greater than 3. Okay. The ionization of the capillary wall can be enhanced by first running a basic solution such as sodium hydroxide or potassium hydroxide through the capillary prior to introducing the buffer solution. And why this is needed, I have already explained you, because this will allow you to generate more and more silanoid groups. Okay, attracted to the negatively charged silanoid groups, the positively charged cations of the buffer solution will form two inner layers of cation, called the diffuse double layer. Okay, so this is regarded as the electrical double layer. Okay, electrical double layer or the electrical double layer. Okay, on the capillary wall as shown in figure this one. The first layer is referred to as the fixed layer because it is held tightly to the silanoid groups. The outer layer, called the mobile layer, is further from the silanoid groups. The mobile cation layer is pulled in the direction of the negatively charged cathode when an electrical field is applied. Since these cations are solvated, the bulk buffer solution migrates with the mobile layer, causing the electroosmotic flow of the buffer solution. The rate of EOF is dependent on the field strength and the charge density of the capillary wall. The wall's charge density is proportional to the pH of the buffer solution. The electroosmotic flow will increase with pH until all the available silanols lining the wall of the capillary are fully ionized. Okay. Other capillaries, including Teflon capillaries, also exhibit electroosmotic flow. The EOF of these capillaries is probably the result of adsorption of the electrical charged ions of the buffer onto the capillary wall. Okay. So, what is the advantage? During a laminar flow, you will find that at the center the velocity is higher, and as you go towards the capillaries, there is a curved movement. There is this parabolic kind of front which is moving. However, in the electroosmotic flow, you will be having in the bulk phase a straight front. So the solvent moves as a packet, as a rectangular like packet. It moves something like this, and due to this reason, what happens is that, so if you see, so we are having two kind of things. Initially, when you are applying this thing, the anions and the cations, they are rearranging, and along with that you are having the electroosmotic flow. Okay, so combining these two, what you will be getting is that you will be getting the illusion of the analytes, sorry, in a sequential manner, uh, through this cathode end. Okay, and you will be able to analyze those stuffs using this detector. Are you getting my point? Now, what is the advantage of this one? The advantage of getting this kind of flow behavior is that there will be, when you are having the laminar flow, the peak broadening of the analytes will be higher. Okay, whereas the peak broadening will be very restricted in the case of electroosmotic flow. Okay, so applications, capillary electrophoresis may be used for the simultaneous determination of the ions NH4 plus, sodium ion, potassium, magnesium, sorry, there should be 2 plus on the superscript, Ca2 plus in saliva. Okay, now this is cost effective approach to do DNA sequencing. So what happens, first we do the amplification, and then we go for the detection of the DNA fragments using the polymerase chain reaction, which has led to rapid and dramatic advances in forensic DNA analysis. Cost effective approach to do DNA sequences that provides high throughput and high accuracy sequencing information. A specialized type of CE, affinity capillary electrophoresis, utilizes intermolecular binding interactions to understand protein ligand interactions. So I am not going into the details of that one. Okay. The sample is introduced in the capillary via capillary action, pressure, siphoning, or electrokinetically. The capillary is then returned to the source vial. Okay. The migration of the analytes is initiated by applying the electrical field, which I have already told, and that is applied between the source and the destination vial, and is supplied to the electrodes by the high voltage power supply. Okay, usually we apply around 1000 volts per centimeter. Okay, so you can see quite a large amount of the voltage is being applied. In the most common mode of CE, all ions, positive or negatives, are pulled through the capillary in the same direction by this electroosmotic flow. The analytes separate as they migrate due to their electrophoretic mobility and are detected near the outlet end of the capillary. Okay, that I have already told you. The output of the detector is sent to a data output and the handling device, such as the integrator or computer. The data is then displayed as an electropherogram. So electropherogram. So like in chromatography, it is chromatogram. In electrophoresis, it is electropherogram. Separated chemical compounds appear as peaks with different migration times in an electropherogram. Just like chromatogram, you will be getting some peaks, something like this. Okay, so you will be having time and the absorption or the concentration on the y-axis. Okay. So they have high sensitivity and sharp peaks are achieved. Why sharp peaks are achieved? This is because the type of the flow. Okay. There is another kind of analysis which is called isotachophoresis. Uh, it is a process called field amplified sample stacking. It results in concentration of analyte in a narrow zone at the boundary between the low conductivity sample and the higher conductivity running buffer. Okay. Then one of the major problem over here, as I told you, we are using capillaries whose diameter is quite low. So because of that, what happens is that we need to increase the path length, because if you remember the UV visible spectrophotometry, we called absorption equals to A, B, C, where A is basically molar absorptivity, and then B is the path length. Now, the path length over in a typical UV cell, what we discussed, was nearly 1 centimeter, but herein we are having very narrow this thing. So, because of that, the reason, in capillary electrophoresis, we can use a bubble cell or a Z cell, where we can have additional tubing, so that we can get an higher amount of liquid in a typical zone, which will allow us in the reproducible measurement of the system. Okay. So in this way, we basically improve the path length by increasing this volume in this bubble cell. So we are increasing the volume, and over here we are measuring the light. And over here, if you see, we are increasing the length, and from this direction we are measuring the optical density, okay, or the absorptions. Then fluorescence detection can also be used in capillary electrophoresis for samples that naturally fluoresce or are chemically modified to contain fluorescent tags. Okay. In order to obtain the identity of sample components, capillary electrophoresis can be directly coupled with mass spectrometers or surface enhanced Raman spectroscopy. Okay. So with this, we complete this topic on capillary electrophoresis. Okay, I hope every one of you have understood the student today's lecture. So I will stop today over here.